we are, let's define here some sigma value, how far we are from this query point, which is always centered at the position 0. So if we are like 5 units, 5 distance units of that point, our activation is going to be around this value here. It's going to be around, let's see, it's going to be around 0.2. If it's more, it's like 10. That's going to be like almost 0. If it's very close to 0, the distance, take a look at the y-axis. It's going to be very close to 1. Okay, so let's go back. So here we have the distances. And using that distances, we're going to apply exactly that Gaussian function using 2 times sigma squared, and that's going to bring the activation function. And the activation function is going to give us, is going to provide us some weight. I mean, the relevance a neighbor has. So if that weight is close to 1, the relevance is high. If that weight is close to 0, the relevance is nothing. It's almost nothing. So in here, we're going to do this, having those, we're going to call these weights. I mean, I believe this is better. We're going to have all those weights multiplied using, this in R is the same as a dot product. Let me write here, a dot product. So it's gonna compute the multiplication of every value in W against every value in the class ID. So when I do that, I'm just weighing or giving some relevance to every output value in D. So if some value here has an importance equals to 1, it's going to be okay. That's going to domain the whole classification process. If that particular weight is close to 0, that particular output is not going to influence at all. So here we have this operation. I'm going to make this operation, and afterwards I'm going to divide by the sum of weights. And if I divide by the sum of weights, I normalize the output result. And that's going to be my output. That's basically my output. Take a look. This is my algorithm. A very simple algorithm. But I don't know if it works because we are doing now. So I don't know if it's going to work properly. Okay, we better see. So to see if it works, I'm going to load it. It's already loaded. Data sets here, DWNN is here. I'm going to provide the data set and now the query. Let's see what happens if I give some value that's already in the data set. I'm going to give the value 1, expecting to obtain 1 as a result. And our sigma is going to be a value probably, could be like 0.1. Okay, it's 1, it's good. What happens if I give some value that's not there, like close to 1, but it's not there? Take a look. It's providing 1 as answer. It's not providing 1.1, but just 1. That's not good enough. Okay, but let's carry on. 1.2. Okay, it's 1 yet. Not good. 1.5. Oops, nice. 1.5, that's good. Maybe 1.3. No, it's 1 again. I don't want that sort of behavior. What happens if I just try to increase sigma to 0.2? Take a look now. If I increase to 0.2, the same behavior, 1.3 with sigma equals 0.1, with sigma equals 0.15, 0.2, take a look, 0.5, take a look at 0.5. 0.5 is nice, yeah? Maybe 0.4, let's see. No, it's not that good. 0.3, no, it's not that good. We better increase it, right? Take a look, 0.75. So what I'm gonna do now is something very, very interesting. I'm gonna do this. I'm gonna use 0.75, or maybe increase a little, like 0.8. Let's see what happens, or 0.9, or maybe 1. Okay, this is close enough. Okay, 1. Now I'm gonna do this. I'm gonna try to apply several points here. So let's say we have several queries. Our queries are varying now from minus 5 to +5, but we have like a very large number of examples, like 100 examples here. And we're gonna apply those query points in here. Let's see what happens. First, let's just run it just to see if it runs. Yeah, it's running. So now I'm gonna use like a, let's call here Z, and Z is gonna be a matrix for us. I'm gonna add in this matrix the output provided by our DWNN algorithm, and also the input. So Z is gonna have something like this. It's gonna have itself concatenated with the query and the output value. So Z is gonna be something like this. Let's plot Z to see how it is. Take a look. Z is very nice, in fact. Yeah, isn't it? We're gonna plot now. Let's plot the original data set in red. So you guys can see how that looks like. Can you guys see the red points here, the red dots? So out of those learning points, those training examples, we were capable of estimating this curve. But take a look what happens if we come here and change sigma. Sigma is going to bring a very, very aggressive change in the algorithm bias. And that's something very interesting indeed. For example, what happens if I come to sigma and use like a very large sigma? For example, 50. Now sigma is 50. Take a look what happens if sigma is 50. Take a look, guys. So better do like this, maybe points. Maybe I should plot the data set here. Yeah, first, and then I plot Z. I think that way is better. Take a look. Take a look what happens if we use a very, very large sigma. What happens if we consider a very large neighborhood? Imagine yourself in a very, very large crowd of people. You are like in a heavy metal show, for example, and people around you are going to classify yourself. So, for example, you have a Gaussian function that's going to be as large as the stadium you are in. And everybody there is going to influence your class, your output class. That's going to bring your class to the average value. What's the average value in terms of the y-axis? It's 0. So it's going to bring to 0. That's very interesting. It's going to bring to 0. So every time I try something here, it's going to bring the average value. It doesn't matter. But instead of that, if I come to some smaller value, let's start with 10 now. 10 is not good, but it's nice to see what's happening. I'm going to plot again. Okay, plot data set and plot Z. Take a look now. It's kind of changing. It's kind of getting somehow steep. It's changing a little, but it's not good yet. What happens if we again change, maybe using sigma equals 5, and see what happens? Take a look now, guys. Yeah, it's a little better, but it's not good enough. Okay, maybe sigma equals 2, and plotting again. Take a look. Very nice. take a look at this region. It's gonna behave almost like a sigmoidal function, in fact. Now again, you're gonna change sigma to 1. We know 1 is good. Okay, but it doesn't matter. We're gonna show no matter how. Okay, it's good. What if I try to use some sigma value that's smaller, maybe 0.7. And again, plot. Take a look. Oh, it's good enough yet. Okay, let's get smaller. Maybe 0.5 and see what happens. Take a look. Somehow it's gonna start having some shaky behavior. Okay, again, reducing it to 0.25. Okay, plotting. Take a look. That's very interesting. Why we have this sort of behavior? Because every time we are close in this axis to some value, we are close to that only value, so it is gonna influence our output with its particular output value. It's not gonna combine its value with the other nearby point. So if I go to an extreme situation, not that extreme yet, but okay, I'm gonna use like 0.15, and I plot now. Take a look, 0.15. It's gonna be like a stair. Looks like a stair, right? That's very interesting. If I go to 0.1 and see what happens, take a look now. Now it's a stair. What happens if I try to go with some smaller value for sigma, like 0.01? Take a look what happens now. That's very interesting. It's a stair again, but let's go with sigma even smaller and plot. Take a look, guys. We're not capable of learning anything here. You know why? Take a look at the values for z. I'm gonna get just the 10 first values for z. It was capable of memorizing what was learned. It was capable of representing the training set. It was capable of providing 0 error for the training set, but it wasn't capable of generalized learning. That's why I've got like not a number for the other examples. Take a look here. If we get like more, 20, the first 20, take a look. It was capable of providing the correct answer for the point that is in the training set. Somehow this is very close to what is in the training set, so it could provide an answer, but for the others, no. That's exactly like a student that has just studied using a single book. He or she knows the book by heart, and if we try to answer, to ask like something that's a little different, a little out of that lane, the answer is gonna be not a number. It's gonna be nothing. You know what's happening here? Let's go back. Every time we have the distance weighted nearest neighbor with a very small sigma, the space of the admissible function grows. It's capable of reconstructing very, very complex functions. Every time we increase sigma, it's gonna use a smaller bias. And if at the limit we decide somehow to use a very, very large sigma value, it's gonna tend to contain a single function inside its admissible space of functions, which is the average function. Remember, if we try here, and what's very interesting for R, I mean, R is kind of a, let's say the mathematics is different for R because it's got the infinite, and the infinite is definite here. What's very interesting. Okay, so if I run with this infinite and plot, you guys are gonna see things tending to the average. That's basically a bias containing a single function containing